So I have to record lecture reviews for 11 and 12, but I'll do that over the weekend probably. Yeah, do you guys know about the videos? Okay, yeah, the YouTube videos. Okay, good, good, good. Yeah, yeah. Yeah, those are made for you guys. It does not help me in any way. Yeah, yeah, well, I'll do my best. Where's Yafet? Where is this guy? Okay, well, he's dead. Well, he can come in at some point. Okay, I guess I want to start with, are there topics that are confusing, first of all, from Monday and Wednesday, that are like you looked at them and you were like, oh my God, what is happening? Yeah. Yeah, like anything about enzymes, enzyme kinetics. Is there anything about those that you were like, what the heck is going on? Yeah, Wednesdays was today. I sure hope you remember what you did today. Yeah, that sounds about right. Okay, I'll try and go over what's important, like I usually do, and I'll pick out what I think you should know, and then if you guys have questions, just start yelling at me, and I'll try and answer them. Um, so yeah, form is here. Obviously, fill that out when you get the chance. But yeah, yeah, yeah. So yeah, OChem jump scare is funny. I think this is just a fancy way of saying that a lot of reactions require energy, right? And just like, your body also has reactions that require energy. When you guys are doing glycolysis, you'll find that step one, so going from glucose to glucose 6 phosphate is an example that actually requires energy. How do we get around that? We couple it to ATP. That's something you'll learn a little bit later, but this is just a fancy way of saying a lot of reactions require energy. They will not test you on the SN2 reaction. I promise you that. They will not test you on SN2. It is helpful, though, to kind of remember how it works. Just very briefly, right? Just know that these reactions occur and, the general mechanism, but I wouldn't be too bothered about it. Um, yeah, okay, so this is the other thing. Spontaneous and unequal speedy. We have two constants. We have delta G and we've got K, right? So delta G, right, all delta G tells me is the energy difference between this position here and this position here, right? It does not tell me how fast the reaction has gone, right? That only tells me the energy drop, nothing about speed, okay? Other than that, I don't think there's really much here to know about. The transition state, right, is this point up here where we're at this very high point energy, right? And then we have this activation energy, right? So this right here, right, is showing you how much energy is required from the ground state to get up to that activation energy so that we can actually do the reaction. Good? Okay. So if we take a look at this, how to speed up chemical reactions? Use enzymes, right? So your body obviously does not just not. It has enzymes for some things, and sometimes it doesn't have enzymes. But generally speaking, there's enzymes for everything, right? So, and what enzymes do is they lower the activation energy, right? And that actually inherently speeds up the process. And there's an equation that I'll go over there. I don't think you have to have that equation memorized, and I think you guys have an equation sheet on your exams, question mark? Is that true? You guys have an equation sheet? Yeah. It's on the back page, right? Yeah, okay, you should have an equation sheet. But just be aware that, they love asking about these enzyme questions, right? Um, what does an enzyme do? Lowers the activation energy, right? And then what does that do? It tends to speed up the reaction, and we'll talk about why it does that in a second, right? Um, any questions about this stuff, this slide in general? Is that a good thing? It's a good sign to move on. Okay. Um, but yeah, like here, like E lowers delta G, right? So it lowers this position here, right, down to this position, right? And then you have this equilibrium, right, where you have the enzyme plus the substrate goes into enzyme plus the product. In reality, it's more like enzyme plus substrate goes into enzyme substrate, which goes into enzyme plus product, right? And this is very important for Michaelis-Menten. Michaelis-Menten is based off of this whole scheme here, right? So if you can understand how this scheme works, you'll never have to memorize anything about Michaelis-Menten ever again. So, and I'll explain that in a second. So, cool. Great slide. I'm sure it's really fun for the professors, but this is just a fun way of saying that enzymes make things fast and they work at many different pHs and temperatures and all that jazz. Um, the ones I think the things that I would very highly focus on here is this specificity, right, for the reactions. I will guarantee you on the exam that they will ask something about catalytic mechanism, right? And like why can't you use why does this chain of amino acids not work for this enzyme or something like that, right? I think on your exam you guys recently had something about like like antibiotic, right? That was D amino acids, right, enzyme specificity, right? Enzymes do not like D amino acids. They L amino acids. Yeah. Yeah, right. Yeah, it was on the exam. It was the first page. It was the last question of that 20 amino acid sequence. Yeah, so just hmm, correct. Yeah. It doesn't. So one of the possible answers you could have said is that it's an antibiotic because the enzyme's proteases cannot recognize the protein. That is one of the options you could have put. Nope. Enzymes are chiral, right? So if enzymes are, in order to produce chiral products, you need to have chiral enzymes, right? It does, but your body uses L amino acids, right? You would need I don't think you have to know that specifically, but you would need some sort of enzyme that is capable of recognizing the D amino acids configuration over the L amino acid configuration, which is not what our DNA encodes. Our DNA encodes specifically for proteins that identify L amino acids, right? And naturally occurring in, I believe, I can't think of anything that has D amino acids in the world. I maybe with one or two organisms, but I can't think of any. L amino acids, it's L amino acids and D sugars, right? So you guys will do sugars later. Yes, sure, yeah, yep. L amino acids. I think the question was more so asking about why doesn't the this D amino acid sequence get recognized by the bacteria, right? And the better answer would be that the the bacteria doesn't have any proteins that are capable of recognizing D amino acids because it's mostly made out of L amino acids. Or sorry, not mostly. It is made out of L amino acids. Yes, but the antibiotic was D, right? So the issue is there that because the antibiotic is D, the antibiotic can go kill the bacteria. Then the bacteria can kill the thing. Yeah. So yeah, but anyways, that was a long tangent. Anyways, they do ask things like this, right? One of the questions on my exam was asking about here is an active site, and they gave you a bunch of amino acids in an active site. What binds to this point? What binds to this point? And it's just like you're supposed to use your knowledge of intermolecular forces to figure out what parts of a peptide chain would bond to certain parts in a protein. So, like for example, if I had a protein, right, and and the peptide had a bunch of like some amino acids in it, right, and the protein had an aspartate, right, a negatively charged amino acid, right. What interactions would I expect between this aspartate and the peptide protein I was given? Well, I would hopefully expect to see some sort of maybe ionic interaction, right? Maybe a hydrogen bond, right? So basically, being able to pick out different interactions is how you get good at those types of questions, right? So if you know those interactions like the back of your hand, it becomes very easy, and those should be free points, right? You want to try and get as many free points as possible on these exams because they're a time crunch. They're a time crunch and they're annoying. So the faster you get at these questions, the easier the exams become, right?
How many questions each exam? You can do like
I would say so. So like the five that I talked to you, I can't remember what they were. Like the 5 2-pointers at the very end of the exam that were talking about like myoglobin versus hemoglobin. Those those should be free points, right? Because it's just one word. Is it this? 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 Right? Those you should be spending like 5 seconds on minimum, like maximum, right? And then you should move on to the things that take more time, right? Like your guys' amino acid question where you had 20 amino acids in a chain, that takes a little bit longer, right? It didn't have as many parts, but it does take longer because there's more amino acids, right? So being able to prioritize time is very important, right? Um, but yeah, other than that, the other things to mention here are that enzymes can be regulated by other enzymes and other proteins, right? And they can be made slower, faster, all sorts of things. And when you guys start covering glycolysis, gluconeogenesis, all that stuff, you'll talk about what makes things faster and makes things slower. Um, any questions about these terms? These terms you just kind of have to memorize. Hopefully it makes a little bit of sense. The active site is the place where the reaction is catalyzed, right? The substrate is the thing that you're turning into a product, right? The cofactor can be a bit weird. A cofactor is basically just a thing that helps the enzyme do its job, right? So like an example of this would be DNA polymerase, which you guys are at least somewhat familiar with, right? In order to actually bind ATP, DNA polymerase needs magnesium. And why does it need that? Because there's an ionic interaction between the phosphate backbone and the magnesium 2 plus ion, right? So you actually can sometimes predict what the cofactor is or could be based off of what the substrate is, right? So that's something they could also ask you about, right? They could ask you like without you guys, because you guys don't cover DNA polymerase in 440, but they could ask you what could a possible cofactor be for DNA polymerase, given its substrate is ATP, right?
which
You don't. So they cannot say, oh, you didn't say magnesium, you're wrong. You're right. I know it's magnesium because in 441 you talk about why you talk about that's magnesium, right? But you could have said iron, you could have said zinc, right? You could have said any of them, right? So as long as you said a 2 plus ion, you should have been correct if I had asked you that question, right? Um, there's also coenzymes, right? NAD plus and FMN. So the difference between coenzymes and cofactors is that coenzymes are often organic and cofactors are usually metals, right? That's the main thing you should keep in mind. Um, but yeah, other than that, I think that's the main thing. It's like inorganic ions here, right? Organic here. Holoenzyme versus apoenzyme. Um, holo means whole, right? So it's just a way of saying the substrate combined with the actual enzyme. That is what a holoenzyme is. It's when the substrate and the enzyme are bound together, right? And then apoenzyme is when the it's just the enzyme. There's no cofactor, there's no substrate, there's no nothing, right? So yeah, so catalytically active, right? Enzyme, and then cofactor is not bound, right? And I think I also want to be like because sometimes, and it seems like here that they actually don't include the substrate. It's mainly talking about cofactors here. So I guess like I'll take back what I said there. They specifically want you to think of apo and holoenzymes as whether or not it has a cofactor or it doesn't have the cofactor, right? So like a holoenzyme would be the enzyme plus its cofactor, right? And the apoenzyme would just be the enzyme without the cofactor, right? So that was my mistake. Sorry about that. Okay, these I'm just gonna be honest. You need to memorize these. At least the names, right? Hopefully, it's at least somewhat intuitive. Like if you took OChem or Gen Chem, right? So like oxidoreductase, right? An oxidation reaction, right? A transferase, transferring one group from one position to another, right? Isomerase is like taking a molecule and transferring it into a different isomer, right? And then polymerase is kind of the weird one, I guess. It's building. Like DNA polymerase. It builds DNA. That's kind of the main thing there. Does that make sense? Yeah, it's a lot of vocabulary I know, but it's gonna get worse when we start going into the pathways. So, but yeah, we're all good there. Yeah. Yep. Okay. Um. All right. Okay. This this is yeah. This is kind of important. So rate constant, right, is how we determine speed of a reaction. So I said delta G, right, determines the energetics, right? Whether or not we lose or gain energy going from reactant to product, right? Tells us nothing about speed, right? The rate constant tells us about speed, right? And the rate constant does in fact use delta G in the equation, which makes sense, right? Because if you have a lower activation energy, you would expect it to take less time, right? Because if you need less energy to actually overcome that barrier, right, you're able to go through that reaction quicker, right? So that is why it's in the term. Um, I have personally never seen them ask a question on this, but it theoretically could happen, right? They do when you guys with McCallus-Menten, there's K-cat and Km, right? So there's K-cat and there's Km, right? So we talk about how fast does the enzyme catalyze, right, versus how well does the enzyme bind, right? Those are two different things, right? And I'll talk about those later. Or if you guys have questions on them, feel free to ask. This did show up on my exam, actually, the difference between Kcat and Km, and what constitutes what, like, and what affects what, depending on a protein structure. So if I gave you a structure of a protein, right, and I told you um, that this certain amino acids were required for binding, but not for catalytic activity, you would say that they would affect Km and not Kcat, right? If I mutated one of those enzymes, would it affect Kcat or Km? It would affect Km, but not Kcat because they're important for binding and not for catalyzation of the reaction, right? Does that make sense?
Vmax.
It would not affect. It would not. So what is Vmax is dependent on Kcat.
Also there.
So it would have no bearing on Kcat. It would change Km though, in my hypothetical situation.
So mutations not.
It depends on where the mutation is, right? So if the mutation is affecting a binding amino acid, an amino acid that helps bind a substrate, then it has no effect on Kcat. If it does mutate an amino acid that helps with catalytic activity, then it does affect Kcat and inherently affects Vmax, right? So it depends on the situation, right? And they do love questions like that.
Are Kcat and Vmax?
They're not the same. They're not the same. Very briefly, Kcat times the substrate of enzyme is equal to Vmax, right?
Right.
So they are not equal. They are proportional.
That in proportion.
They are not equal, right? Because you need your enzyme concentration. I can't remember. I think on my exam I had a question like this that asked me to do some weird math with this. But just be aware that the second exam is a little bit more math heavy, right? Just because of how much McCallus-Menten is on there. Right. So here's the scheme, right? Actually, it's clearly right there. So if you have if you without the enzyme, right, you have some rate, right, catalyzed by like not an enzyme, right, and it's just dependent on the amount of substrate, right. When you catalyze it, right, it's a different rate, right, and this Kcat is dependent on delta G as well as some other factors, including temperature, right. This slide is a bit weird. I don't think you need to know very much about it. Right. I think there's more important things to study than this slide, but just be aware that enzymes speed up the reaction, and then the Kcat is of an enzyme is dependent on the amino acid groups within the enzyme itself. Right. Does that make sense? It's a lot of information there. Yeah. Okay. Okay. Nonsense. I honestly don't care about how they go through all this math. Okay. Um, I feel like there's more important things to go over. So yeah, I mean, I think what they're trying to say here, you know what? No, I don't want to make it more confusing than it already is. Yeah, I think it's easier to go past it. Um, so right, so the thing here, right, is substrate specificity, right? Like I talked about before, because amino acids are made in a certain way, right, and substrate proteins, right, are evolutionarily made to bind certain substrates, right? And they are built like that so they can catalyze reactions that are hopefully helpful to us and not deleterious, right? So they have to be complementary, right? Complementarity. Yeah, complementary, right? In the sense that one shape has to fit into the other shape for the reaction to actually take place. Because if that doesn't happen, they just don't fit together and nothing happens, right? So the idea here is that any given enzyme should only really react with one substrate. It might react with other substrates if those substrates are all structurally similar, right? But the idea is that there should be like no side reactions. A lot of diseases actually come from enzymes that are faulty, and then you end up with products that aren't supposed to be there, right? So that's just something to be aware of. And the substrate orientation does matter, right? So like the substrate has to be positioned in a very specific way for it to bind to the enzyme, right? Think about like a lock, right, in a key. I'm sure they've used this before, right? A key has to be placed and turned in a specific way for the actual door to unlock, right? You can't just put the key in and go, ooh. You got to turn it a specific way. You got to hit certain buttons, right? Same thing with enzymes, right? They need a specific shape and they need a specific shape and a specific orientation, right? This is just an example of it. I wouldn't be too worried about this. Again, I feel like they put a lot of stuff in these slides, and I don't think all of it's very important. I think like the exams tend to be a little bit more um centered around testable content that involves like enzyme mechanics and like Michaelis-Menten on the second exam. I can't remember off the top of my head what the rest of it's on, but I will definitely go back and take a look because it's interesting. Um, Same thing here. Again, I oh I personally actually scored lower on the second exam um than the first one. I think the average was higher though. I think it was actually much higher.
Very
Yeah.
small. So it's like
You guys are gonna start doing glycolysis and gluconeogenesis, I think. And then you guys will do glycogenolysis and glycogenesis. Huh? Is that for your third exam or for your second exam? That's for your second, right? Yeah, that was my second. Also included. It basically included all the Michaelis-Menten, um, plus like enzyme specificity, plus glycogenolysis, glycogenesis, gluconeogenesis, and glycolysis. Enzyme specificity is under that umbrella of Michaelis-Menten, basically, plus plus enzyme kinetics, right? It's all in there, right? Um, but yeah. Um, Again, just this idea, right, um that enzymes stabilize transition states, right? So if there's no enzyme, as an example, you have a metal stick, right? You have a transition state, and then if the products are here, right? But the issue with this is that if you think about trying to break a metal stick, I don't think any of us can break a metal stick. I'll be so honest with you guys. So you can imagine that it's not going to work, right? However, if I take a hydraulic press and I use that, right, as my enzyme, and I smash the metal stick, then it's probably a bit easier for me to break the metal stick, right? I have to put less energy into breaking the metal stick to actually break the metal stick, right? So that's the whole idea here. These graphs, I think just be aware of the fact that the enzyme substrate complex is quite stable. Um, and that once you form that complex, you end up dropping this activation energy so you can actually do the job that you're hoping to do. Yes, okay. Believe it or not, guys, acid-base stuff does come back. So I sure hope you remember your OChem and Gen Chem. Because serine proteases and stuff do show up. Um, I don't think you have to I didn't have to memorize them personally, but like this is like remember that like there are cases where they'll give you an active site, right, and they'll ask you about the different amino acids inside of the protein. So this is what I was talking about. Like they might give you a serine protease and be like, "Oh, what does this amino acid do? What is it likely to do?" Right? Stuff like that. Um, so right. So the big thing here, right, is that acidic groups donate H plus, right? And basic groups, let me use a different color here. Basic groups accept H plus, right? Hopefully that makes sense based off of what you guys know about amino acids. But sometimes when you have 8 billion amino acids inside of a complex, it can be a little bit daunting and kind of scary to figure out what's going on. The main thing is, right, that these acidic and basic groups are there to do their job. And their job is to stabilize these species, these substrates that are there. Because if you stabilize a substrate inside of the enzyme, it's not going anywhere, right? And what you want is for the enzyme to hold on to the substrate and actually turn it into a product, right? If you don't have some of these donation and acceptance reactions, right, sometimes it doesn't happen, right? So just something to be aware of. Chymotrypsin is an example. I never had to memorize these enzymes. Um, just be aware, I guess, of them. I don't think they did they say anything about whether or not they're going to test you on the exact like the specifics of proteases and stuff.
So, oh,
I don't remember them saying anything like that. So, okay. Yeah, it also, just for reference, if you don't know what protease is just something that breaks apart proteins, right? So, it cleaves peptide bonds, through active serine site, right? And here's an example of how this works, right? So, if you remember your OChem, right? We got a nucleophilic attack on this carbon, right? So first we have to deprotonate, right? So when we deprotonate this H, right, we develop a negatively charged species, which is very reactive, right? And then this attacks this carbon, right? And then this nitrogen group gets kicked off, and that basically separates the peptide chain in two, right? And then this eventually, serine will get protonated again by something else, and then it'll release this peptide chain, right? Does that make sense? Right? They could 100% ask you questions about, like, what is the function of this serine? Or what is the function of this base? This base is often something like histidine or lysine or something, right? Something that has a lone pair some of the time, right? That's able to grab that hydrogen off, right? So you should be thinking about what kinds of amino acids do I need that can actually remove that H, right? What kinds of amino acids can I use to remove that H from this case, right? So right? So serine, right, is obviously not generally acidic, right? The pK of serine is like 16. It's ridiculously high, right? The pKr can change dependent on what groups are around it, right? So generally speaking, right, if you have a basic group around it, right, it's probably going to be more like it's going to be deprotonated possibly more often, right? Just be aware that it sometimes changes depending on the active site, right? Um, yep. So we said this before, right? They use them as donors, as acceptors, right? They may provide, different things that alter values here, right? Um, other than that, I don't think there's really much. I would say these are the main amino acids you'll see inside of enzyme active sites. Those are the main ones, right? And the reason being, you know, these are the basic form is a good proton acceptor, right? Um, This one's a good proton acceptor, right? Actually, I'm sorry. This is generally a good proton donator. Sorry. This is generally a good proton acceptor, right? Also, generally a good proton acceptor could possibly be a proton donor, right? Um, this histidine generally acts as a base, right? Also acts as a base, right? And then also tends to act as a base. So you have to be aware, right, that it can be in either of these forms, right? Um, and depending on which form it's in, is kind of what determines what it does in the active site, right? So if it's negatively charged, it most likely acts as a nucleophile of some sort, right? Or it grabs a proton from somewhere, right? If it's already got the H on it, it probably acts as a donor of some kind, right? Maybe it donates a proton. Maybe it forms a hydrogen bond, right? So just things like that. And this idea of covalent catalysis is just that if you look up at like the serine protease, right? Believe it or not, you have to form a covalent bond in order to actually do this reaction, right? So notice how here there is no bond here between the serine and the protein, right? But then in this step there is a bond between the two, right? So that's just what they mean by covalent catalysis is that there needs to be like some sort of intermediate that has a covalent bond between the substrate and the enzyme, right? And the serine protease is an example of that, right? Here's another example, right? We have our serine, maybe a threonine, right? And then we have this acylation reaction where we basically take this tack here, right? Kick this off, right? And you end up with this, right? Do we see how that works there, right? And then when we do deacetylation, right? This water comes in, kicks that off, and then this goes there, right? Are we following so far on that? Yeah. So they won't ask you to do arrow push notations for this, but I think being able to do arrow push notation is very helpful, right? Because it's all just OChem, and I think it's a lot easier to try and understand how this works rather than memorize it because there's too many different mechanisms to worry about, right? Just be aware of that. Um. Oh, okay. Yeah. Cool. We just talked. Yes, electrophiles and nucleophiles, right? If it's got a negative charge, probably a nucleophile, right? If it's got a carbonyl group like this, probably an electrophile, right? If it's got a plus charge like this, probably an electrophile, right? Phosphorus, right? Because it's being pulled in so many different directions by these oxygen atoms, right? Probably more of an electrophile, right? Um, and then obviously a proton is going to be an electrophile because it has no electrons, right? Um, but yeah, this all makes sense, right? These aspects here. This is just a lot of OChem review, basically, right? Yeah, this is just another way of saying enzymes require metal. The cofactor idea, right? So some enzymes require things like magnesium, zinc, sometimes sodium, maybe all these all different things, right? So yeah, they help bind organoids. So here's an example. Oh yeah, here's an example actually. Yeah, so like see, notice how these magnesiums, right? They're kind of binding to these O's, right, and stabilizing this, right, in this state here, right? So yeah. Other than that, I think that's honestly all I want to talk about for this lecture. Any questions about this before I go into lecture 12?
So you said we don't need to know much about the equation, right?
I don't think you need to know much about those equations that they brought up there. I think there's more important equations. Like the Michaelis-Menten equation.
Really?
The Michaelis-Menten equation is so important. The Vmax equals kcat times enzyme concentration is important. There's some inhibitor equations that I have to go over again because it's been a while since I've done them. But those are also pretty important. Um, but yeah, I think that the most important one for sure is the Michaelis-Menten equation. Okay. So yeah, here we go. Yeah. So here was your exam. Cool. Have fun. Here, yeah. So my exam was this one
Yes.
on,
Over on the mostly 75.
yeah, for your guys's or mine. Oh yeah, on mine. Yeah. Some people did get a pretty dang high. So yeah, you got a 94. You guys got yeah. So a decent amount of people got 95 actually, like 6 or 7. But
But a lot of people had 95.
yeah. So we got like we got a decent amount of people who got, which is interesting. I guess the back end, yeah, I mean, it ripped to the guy who got a 15 on our exam. So but I hope that's none of you. So but yeah, I mean it is what it is. So yeah, our average is a little bit lower. So I was in this range here is where I was at, right? Yeah, so I yeah, so I was a little bit above that. I was at 86. But yeah, I got an 86 on the first one, I got an 83 on the second one, and I got 87 on the third one, and then I got a 91 on the last one.
We do it all.
Yeah. The final is generally relatively difficult, yes, because it's 50 minutes, right? But the nice thing about the final is um people who people who don't need to take it won't take it, and it's usually the smarter guys, right? And so what ends up happening is like people who need a grade boost try and take the final, and it's just kind of bad, and so they don't do as well as they want on it. And so if you manage to do well on it, you get a massive boost because it's a competitive grading scale, right? I know they don't say it's competitive. It's competitive. It is competitive. So it is competitive. Unless they like set certain bins for certain percentages, right? It is competitive, right? And I don't think they did that for biochem. So
So, what score do you think we need to get to be able to secure like a above and through the lot of million base on?
I would say if you consistently score, what was my exam average? I would say it depends on the year, obviously. I feel like if you're able to score around 80s, you might be able to drop into like maybe like a high 70 at some point, right? And you can probably get it. You can probably get a 3.7, right? Basing that off how my exam scores went.
It's 70.
Yeah.
What would you
Someone take the average of my exam scores for me. It was eight
get for the bronze?
3.9, right? Yeah. So, huh? Great question. I have no idea. Huh?
Isn't that close to my?
No, it's not close to a 95. No, it's definitely lower, but I can't remember off the top of my head. I would just take whatever my exam average was and then like say, okay, how much higher or lower than this do I have to be to get a certain GPA? Because it's mostly dependent on exams, plus the quizzes,
You
but
said you were trying to keep the mean.
yeah, they generally try and do that. So again, another way of saying that it's a competitively graded class, right? So, but yeah. Anyways, this is a long one. I'm not sure if I'm gonna be able to get through all of it, but we'll definitely try. Um, yeah, I feel like there's a lot of stuff in here. Um, and I don't, yeah. So, yeah, so why measure the rates? It's basically just a way of figuring out how fast the enzyme does things, right? That we need to know how quickly an enzyme is able to churn out products, just because a lot of our science and our tech is based off of whether or not we can calculate the enzyme's affinity and like how fast it's able to do things. Um, you might use this in a lab. Depends on what kind of lab you do. If you do a biochem lab, you probably will. But it's not guaranteed. But I mean, if you a rate, right, is just a change in something over the change in time, right? And in this case, it is the change in substrate over the change in time, which is also the change in product over the change in time, right? So the substrate should be converted to the product at some rate. So right, so the same rate that you're depleting the substrate should also be the same rate that you're increasing the product, right? Don't really think this is that important. This whole thing about like measuring how rates change with certain things, like with pH, right? Sometimes it does change. Just be aware. They can test you on it. Um, yeah, I honestly don't think this is that important. I want to get to the actual like equation. So yeah, okay. So the idea is right. In the presence of like a consistent and constant amount of enzyme, right? Initially, right, you're gonna have this straight linear increase in the speed at which the enzyme is able to produce product with respect to time, right? That initial rate is linear, right? It's relatively easy to calculate something that's linear in terms of its slope. You just take the rise over the run, right? So 2 points, right? And you subtract those y values and those x values, and you're able to get that change over time very easily, right? Unfortunately, though, enzymes are not that nice, and they do actually plateau at some point, right? So the yeah, so basically, right, this plateau, like, why does it happen? Because you only have so many enzymes, right? You only have so many enzymes, or you don't have unlimited enzymes, right? If you had unlimited enzymes, then it would just go to infinity, right? But because we have only a certain amount of enzymes, right, you can only produce a certain amount of product per second, basically, right? And yep, once all the substrate has been turned into product, right, there shouldn't be any more enzyme catalysis, right? All the substrate has been changed. There should be nothing left, right? So what we do to combat this, right, is we basically try and we take the maximum rate. So the maximum rate would be somewhere during this linear section, right, of the enzyme. So this whole V naught equals V max times substrate divided by Km plus substrate, right? That V max, or that V naught you're solving for basically, yeah, basically comes from this, right? So we're basically taking the linear point of a curve. Does that make sense? Okay. Right, so we measured a single rate, right? Based off of a specific concentration of substrate, right? Now all we have to do is we have to add increasing amounts of substrate, right? And we can take these points, right? These individual points that are straight, right? and then we can plot them, basically, right? That is how we develop these Michaelis-Menten curves. So you can see here, right? We took this linear point here, right? This linear point here, and this linear point here, right? And we're using that, right, to plot some sort of curve, right? So we're saying, what is the initial velocity when the substrate is 0.2? It's going to be here. 0.5, it's here. 1.0, it's here. And we're basically doing that for the entire curve, right? I won't bore you with how this works because I feel like this is I don't think this is that important. Just be aware that this is a thing though, and they could theoretically test you on like how do we come up with our Michaelis-Menten curves. I think that's a little bit too I think it's a little bit too memorizey. I think there's more things to test understanding on, but this is the thing they could do. Yeah. Okay. So these two equations would memorize. Hopefully it makes intuitive sense though. This one probably not. This one's a bit weird, right? But hopefully this one makes a little bit of intuitive sense, right? The maximum rate of any given reaction is based off of how fast the enzyme catalyzes the reaction, and two, how many enzymes do you have, right? That should hopefully make a little bit of sense, right? Because the maximum velocity should be dependent on how many enzymes you have, and it should be dependent on how quickly the enzyme is able to do a reaction, right?
Why?
That's a good question. I think the thing the thing to keep in mind is that with Vmax, right? We are trying to think about the if you have a given amount of enzymes, because the enzymes are what set the maximum rate. The substrate will decide the rate that you're at, right? But the maximum rate, the absolute maximum that you could reach is dependent on the enzymes. The substrate, right, will determine the initial rate given that concentration of substrate. Does that make sense? So the substrate determines the initial the rate with that given substrate, but the maximum possible velocity you could have is only based on the enzyme concentration.
Mm.
Does that make sense?
Okay.
It's like I'm trying to think of an analogy for it, but I can't.
Because if we're at Vmax, it
Mhm.
doesn't know should be added.
Right, exactly, because it plateaus. Right? It doesn't matter how much you add, right? You're going to be plateauing anyways, right? It's like saturation, right? Because the enzyme eventually saturates, you can't add any more the more substrate you add doesn't matter, right? Because you've already saturated all the enzymes you have. Right? I think that's probably the best way of thinking about it, right? Because you have saturated all the enzymes that you have, it doesn't matter if you add more substrate, right? Because all the enzymes have been taken up, basically, right? Does that make sense? It's okay to say no as well. Okay, I will move on, but if there are questions, feel free. This equation, just memorize it. It's on your equation sheet, I think, right? But I would say, like, the more things you can memorize in terms of these equations, the less time you spend flipping back and forth between your equation sheet and your exam. I was this equation or just the whole thing. You should know that this Michaelis-Menten equation is just generally quite important. This is probably the most asked about equation in terms of Michaelis-Menten, just because it explains how Michaelis-Menten works, right? Basically, these curves are derived based off of this equation, or like this equation is derived based off of these graphs. They did on my exam. I can't remember off the top of my head like how they work exactly. I was trying to figure out how they work recently, but I might have to take a look at that more when I actually upload the recording for this video, right? When I actually upload the lecture recording. but yeah. Okay, so this scheme is important. So we have the forward reactions to form the enzyme substrate complex. And we have the reverse reaction to go back to the enzyme substrate, enzyme plus substrate, right? We also have going from enzyme substrate complex to enzyme plus product, and we have the reverse reaction. For the case of Michaelis-Menten, we say this guy is not real, right? We always assume for the Michaelis-Menten kinetics that the forward reaction of this second reaction here is just going forward and pretty much only going forward, right? If that is not the case, we basically don't abide by Michaelis-Menten rules and we can't use these graphs and these equations anymore, right? But yeah, these are the ones you should keep in mind. You should keep in mind K negative 1, K1, and K2. Basically, these are the rates, right? So the rates at which these reactions occur. So the rate at which enzyme plus substrate is turned into enzyme plus product. Or enzyme substrate complex. The rate at which the enzyme substrate complex is turned into the enzyme plus product, right? So we have the association reaction, K1, and the dissociation reaction, K negative 1, right? And then we have the production, K2, right, of enzyme plus product, and then we ignore this one, right? Make sense? Yeah, negligible. Cool. Great. It'd be weird if your enzyme decided to take the product they just made and turn it back into something they just had before, right? It doesn't really make sense. So yeah, and here's the derivatives. Great. I'm not gonna bother going through the calculus. Um, I guess I'll try and talk about these assumptions, right? So the first one is this, right? The product is fast and basically irreversible, like I said, right? That's why we don't have the second K2 here. The substrate amount is always greater than the enzyme, right? And that's just this idea we actually want to get to the saturation point relatively quickly, right? Um, it's just to make sure that these Michaelis-Menten curves are basically what we don't want is we don't want the substrate to be limiting because that messes up the graph and we can't use Michaelis-Menten kinetics anymore because it's dependent on the fact that our substrate is infinity for the sake of being simple, right? Yep, yep, yep. And they just do a bunch of derivations here that I honestly don't. Uh, oh, yeah. This is just yeah. This is basically saying that like this reverse reaction is zero. Again, I think there's better things to be worried about, right? Yep, 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 yep. Okay, cool, cool, cool. Yeah, so this is the important part. So this enzyme substrate complex is in rapid equilibrium between going this way or going back this way and turning into this again, right? This is the main thing, right? And it's actually how we determine Km. So Km is actually based on the dissociation and association of this. And yeah, they just do a lot of derivation here. I'm not gonna lie, I feel like the derivation is not what I care about. What I do care about is this. So, Km, right, is the dissociation constant, right? I mean, that's how it was taught to you guys, right? And this is the equation for it. Now, do you need to know the equation for it? Probably not. But is it helpful to understand why that is the case? Yes. So let's look at why that is the case real quick. If we go here, enzyme plus substrate equals, right? Enzyme substrate, right? And then we have K negative 2, K2, K1, and K negative 1, right? Basically, right, Km looks at the dissociation of this. How fast does that complex dissociate, right? And what are the two options we have for dissociation of this complex? So K1 is going to be, I kind of drew these arrows wrong, didn't I? Okay, so K1 is going to be formation of ES, right? K negative 1 is going to be dissociation of this back into this, right? K2 is going to be dissociation of this into the enzyme plus product, right? and we ignore k negative 2, right? So what you'll notice about this is if we want to talk about dissociation, we should be thinking about, okay, k negative 1, right, which is one of the dissociation constants, k negative 1, plus k2, which is another dissociation, right, divided by the association of it, which is just k1, right? That is the definition of km, and that is literally what they're talking about here, right? Yeah? That makes sense? Yes? Okay. This is not, I wouldn't say this is like crazy terrible and they've touched you on this a lot, but I think it's important to understand how they came up with this, because it's not really that intuitive unless you look at how this works. And then they just go on a rant about more derivation about Michaelis-Menten. Um, again, I don't, here you go. Ta-da, here is the equation you want to use. Again, all the derivations. Did they tell you that you don't need to worry about the derivation? They did in lecture, right? Yeah, okay. They told us in lecture as well.
There's this a lot of this. It's like it's important to take away the assumptions, like assumption that K2 is like negative or K2 negative or something.
Yeah, yeah. It is important. It is to take away. Yeah, it's important to like. You should apply the assumptions. Basically, the assumptions are important because if we don't assume them, then and the Michaelis-Menten may as well just not exist. Um, but yeah, that is the main thing here. But I honestly, I'm trying to see if there's anything else that I would like. And here's a nice little slide actually that shows you everything. Right. Yeah, and then they do more. Right. They do more stuff on this. And then kcat, right? So kcat, right? The turnover number, the catalytic, not the catalytic efficiency. Catalytic efficiency is a different thing. So the kcat is equal to this, right? And if you rearrange this, right, it's the kcat equals sorry, hold on. If you rearrange it, it's the Vmax, sorry, equals kcat times the enzyme concentration, right? If you just rearrange this equation a little bit, right? Um, Yeah, so I think the most often thing that they do is they'll give you like an enzyme concentration and like they'll ask you to solve for Vmax given like the Km substrate and like the V naught of a system, and then they'll ask you to use the calculated Vmax to solve for like the Kcat or something, or like to solve for the enzyme concentration, right? If that makes sense. Basically, they want you to do a lot of different steps. Here's catalytic efficiency. Basically, how fast does the enzyme catalyze the reaction divided by how fast the enzyme dissociates from the enzyme substrate and the enzyme product. Right? That makes sense? Perchance? Yeah? It's basically just a way we're trying to figure out how fast is this enzyme able to actually pull it, produce its product, right? Without releasing the enzyme and the substrate into solution and not producing product at all, right? It's just a way of figuring out, hey, is this enzyme efficient at its job? Is it efficient at producing the product it wants? If we have a high kcat, right, it means a high Vmax, right? Does that make sense? Right?
Feedback is good wild.
Right? So if I go back here, if I increase kcat, Vmax has to go up,
Yeah.
right? And you control the enzyme concentration, right? So if you had a kcat that was like 10 billion, right, you could add one enzyme and your Vmax would be crazy, right? So as long as this value is high, right, Vmax will also generally be high, right? That's the main thing there. Does that make sense? Okay. Cool. Yeah.
So you get for constant amount of there.
In what conditions? Like
For
yes, yeah, yeah. I mean the enzyme should be constant, right? So
how important should we know about like the assumptions?
I feel like it's important to know This slide nicely illustrates it. So honestly, I would just go through and, you know, hopefully like these enzymes make sense by the time you review it like 8 billion times, right? Um, but I personally never had them test on like the rules themselves. Again, there's better things to test on. That doesn't mean it can't show up, right? It could show up, but I personally have never seen it.
What is the structures well?
Yep. Yep.
Oh, can you
What, this one?
yes,
DX. Let's see here. The change in substrate.
over Father?
Yeah, the initial velocity, it starts at it. Yeah, I think they're trying to say that the initial velocity starts. I have to actually look at this. This is a.
I think she said the initial velocity when the concentration of that barely changes.
Yeah, that's like when it's first binding to the enzyme. Yeah, so like I think a very like at the very beginning, it probably is close to zero because in a solution you need the enzyme to actually bind the substrate in the first place before it starts. But I'm not too sure about that. I need to double check that. That could be this could be something else. So uh, yeah, this is the other thing, right? So Km is not the same as Kd, right? So with Km, right? Remember we're gonna make with Km we have where did it go? Oh, I can't find it. Uh, okay, well with Km, remember we have that equation, right? I want to find it, bro, because I feel like it's gonna be helpful. Yeah, so with Km, right? Remember we have this equation, right? So we can go either this way or we can go this way for dissociation, right? In terms of Kd, right? There's only two states for like a dissociation constant, right? For a dissociation constant, where the heck did it go? I feel like I'm having an aneurysm going through all this. Yeah, so with just a normal enzyme, right? You have protein plus substrate goes into protein substrate, right?
Right.
So Kd is only for proteins that bind and then unbind. There's no like secondary reaction like this, right? So that's something just to be aware of, right? So that's why Kd is different from Km. And then I guess in terms of inhibitors, I don't think we have time for them. But again, I'll do my video this weekend and hopefully get that up for you guys. I think, yeah, yes, you can. Give me 1 second. I want to see. Yeah, yeah, okay, yeah, that's it. Yeah, I'll post my video for lecture 12 this weekend. Hopefully, if I'm not dying. But we'll see. Yeah, I finished my exams on Tuesday, so we shall see. Alrighty.